The moon hangs in our night sky, silent and familiar, a companion that has watched over Earth for more than 4 billion years. Expand your view to full screen and consider subscribing as we explore one of the most profound transformations imaginable. Tonight, we ask a question that begins simply but unfolds into layers of consequence that touch every aspect of existence on our world. What would happen if the moon were replaced by a planet? The question itself seems almost whimsical at first, the kind of thought experiment that might arise during a late evening of stargazing. But as we begin to examine it with the tools of physics and planetary science, we discover that this scenario opens doorways into understanding just how delicately balanced our world truly is, how precisely tuned the cosmic arrangement that permits our existence has become, and how catastrophically or magnificently different Earth might be under different celestial circumstances. The moon is not merely a light in the darkness or a romantic backdrop for human culture. It is a gravitational anchor, a tidal engine, a stabilizer of climates, a shield against certain cosmic impacts, and a record keeper of the early solar system's violent history. To replace it is not simply to swap one object for another in the sky. It is to fundamentally rewrite the physical conditions that govern our planet's behavior. We must begin by understanding what the moon actually does, not in poetic terms, but in the language of force and motion, energy and momentum, mass and distance. The moon orbits Earth at an average distance of approximately 384,400 kilometers. Its mass is roughly 1/81st that of Earth, which might sound insignificant until we recognize that this makes it extraordinarily large relative to its parent planet compared to most moons in the solar system. The ratio of the moon's mass to Earth's mass is unusually high, and this relationship has profound consequences. The moon's gravity pulls on Earth continuously, creating a bulge in the ocean waters that we experience as tides. These tides are not merely the rising and falling of water at coastlines. They represent a transfer of energy and angular momentum between Earth and the moon, a gravitational conversation that has been ongoing since the moon's formation. This tidal interaction has slowed Earth's rotation over geological time. When Earth first formed, a day was perhaps only 6 to 8 hours long. The moon's gravitational pull on Earth's tidal bulges acts as a brake, gradually transferring rotational energy from Earth to the moon's orbital motion, lengthening our day and pushing the moon slowly farther away. Currently, Earth's rotation slows by about 1.7 milliseconds per century, and the moon recedes from us at roughly 3.8 centimeters per year. This seems trivial on human timescales, but is transformative over millions and billions of years. The moon's presence has thus shaped not only the length of our day as it exists now, but the entire evolutionary history of day length on our planet, which in turn has influenced biological rhythms, atmospheric circulation patterns, and climate systems. The moon also stabilizes Earth's axial tilt. Our planet rotates around an axis that is tilted approximately 23.5 degrees relative to the plane of its orbit around the sun. This tilt is responsible for our seasons, as different hemispheres receive varying amounts of sunlight throughout the year. Without the moon's gravitational influence, Earth's axis will be subject to much larger variations driven by gravitational perturbations from the sun and Jupiter. Computer simulations suggest that without the moon, Earth's axial tilt could vary chaotically between 0 and 85 degrees over millions of years. Such variations would create wild swings in climate, potentially making the planet far less hospitable to complex life. The moon, by its gravitational presence, keeps Earth's tilt relatively stable, varying only between about 22.1 and 24.5 degrees over a 41,000-year cycle. This stability has provided a consistent seasonal pattern that life has adapted to over billions of years. Now we come to the heart of our question. What if we removed the moon and replaced it with something else, specifically with one of the planets in our solar system? To fully explore this, we must consider not just immediate gravitational effects, but the cascade of consequences that would ripple through Earth's geology, oceans, atmosphere, and biosphere. We must think about orbital mechanics, tidal forces that scale with mass and distance in specific mathematical ways, the possibility of orbital stability or catastrophic collision, the visual and psychological impact on human civilization, and the long-term evolution of a planetary system so radically altered. Let's begin with the smallest planet, Mercury. Mercury has a mass of approximately 3.3 times 10 to the 23rd power kilograms, which is about 4.4% of Earth's mass, making it roughly 18 times less massive than Earth, but still about 3.7 times more massive than our moon. If Mercury were to replace the moon at the moon's current orbital distance, the first thing we would notice is that tides would become significantly stronger. Tidal force depends not just on the mass of the orbiting body, but on the inverse cube of the distance between the centers of the two bodies. The formula for tidal acceleration is proportional to the mass of the perturbing body divided by the cube of the distance, multiplied by a factor related to the size of the body being affected. Since Mercury has roughly 3.7 times the mass of the moon, but would be at the same distance, the tidal forces would be approximately 3.7 times stronger. This might not sound catastrophic, but consider what this means. Current tides on Earth, driven primarily by the moon with a smaller contribution from the sun, cause sea levels to rise and fall by several meters in many coastal areas, with some locations experiencing tidal ranges of 10 meters or more during spring tides when the moon and sun align. If tidal forces suddenly increase by a factor of nearly 4, coastal regions will experience dramatically higher tidal ranges. In places like the Bay of Fundy, which already experiences some of the highest tides on Earth with ranges exceeding 15 meters, we might see tidal ranges approaching 60 meters or more during extreme configurations. Such tides would fundamentally reshape coastlines, flooding low-lying areas during high tide and exposing vast stretches of seafloor during low tide. Coastal cities would become uninhabitable in their current form. The rhythmic advance and retreat of water will be violent and rapid, but the ocean tides are only part of the story. Earth itself experiences tides in its solid body. The moon's gravity deforms the solid Earth by about 30 centimeters, creating a bulge that follows the moon around the planet. With Mercury in place of the moon, this solid Earth tide would increase proportionally, deforming the crust and mantle by more than a meter. This continuous flexing would generate significant internal heat through friction, potentially increasing volcanic and seismic activity. Fault lines that are currently stable might become active as the greater tidal stresses overcome the frictional forces holding tectonic plates in place. Earthquakes could become more frequent and more severe, particularly in tectonically active regions. Volcanic activity might increase as the greater deformation of the mantle enhances magma generation and transport. The increased tidal forces would also accelerate the transfer of rotational energy from Earth to Mercury's orbit, causing Earth's rotation to slow more rapidly than it currently does. Over millions of years, days will become noticeably longer at a much faster rate than they are currently lengthening. This would have cascading effects on atmospheric circulation, ocean currents, and climate patterns, all of which are sensitive to the length of the day. The Coriolis effect, which shapes weather patterns and ocean gyres, depends on the rotation rate of the planet. A more slowly rotating Earth would have weaker Coriolis forces, altering the paths of storms and ocean currents in ways that would shift climate zones and precipitation patterns. Visually, Mercury in the sky would appear significantly larger than the Moon. The Moon has an angular diameter of about half a degree as seen from Earth. Mercury, being roughly 3.7 times more massive, but also about 38% the diameter of Earth, compared to the Moon's 27%, would have a diameter of about 4,800 kilometers compared to the Moon's 3,500 kilometers. At the same orbital distance, Mercury would appear roughly 1.4 times larger in angular size than the Moon, subtending an angle of about 0.7 degrees. This would make it noticeably bigger and more imposing in the sky, and its surface, being quite different from the Moon's, would present a different visual character. Mercury's surface is heavily cratered, but also features smooth plains of ancient volcanic origin and unusual terrain patterns unlike anything on the Moon. Its color would be somewhat darker, and perhaps slightly more brownish-gray than the Moon's pale gray. However, we must pause here and consider whether Mercury could actually stably orbit at the Moon's distance from Earth. Orbital stability depends on several factors, including the gravitational influence of other bodies, particularly the Sun. The Moon orbits within Earth's gravitational sphere of influence, known as a Hill sphere, which extends to roughly 1.5 million kilometers from Earth. The Moon's orbit at 384,000 kilometers is comfortably within this region. Mercury, despite its greater mass, would still be well within Earth's Hill sphere at this distance. However, Mercury's orbit will be subject to stronger perturbations from the Sun because Mercury is more massive and therefore less tightly bound to Earth relative to its interaction with the Sun. Over long timescales, orbital evolution might differ from the Moon's, but for the purposes of examining immediate and medium-term effects, Mercury could maintain a stable orbit at the Moon's distance. The psychological and cultural impact of seeing Mercury instead of the Moon would be profound. Human cultures around the world have organized calendars, religious observances, agricultural practices, and mythologies around the Moon's phases for thousands of years. Mercury, with its different size, appearance, and perhaps different reflective properties, would alter these cycles. The phases would still occur as Mercury orbited Earth, moving between positions where it is fully illuminated by the Sun from our perspective and positions where it lies between Earth and Sun, appearing dark. But the visual experience would be different. The light reflected would have a different quality, and the emotional resonance of the night sky would be transformed. Now, let us consider a more dramatic scenario, replacing the Moon with Mars. Mars has a mass of about 6.4 times 10 to the 23rd power kilograms, roughly 11% of Earth's mass, or about 9 times the mass of the Moon. Placing Mars at the Moon's orbital distance would increase tidal forces by a factor of 9 compared to the current Moon. This represents a transition from significant to extreme. Ocean tides will become violently destructive. Coastal areas will be subject to tides rising and falling by tens of meters every few hours. No current coastal city would remain habitable. Ports, harbors, and maritime infrastructure will be obliterated by the regular onslaught of water. The tides would reach far inland, turning river valleys into tidal estuaries, extending hundreds of kilometers from the current coastline. The solid Earth tides would cause the planet's crust to rise and fall by several meters twice per day. This continuous, large-amplitude deformation would generate enormous amounts of heat within the Earth through tidal friction. The effect would be similar to bending a piece of metal back and forth repeatedly until it becomes hot. In Earth's case, the crust and mantle would be subject to such intense flexing that seismic activity would increase dramatically. Earthquakes would become far more frequent and powerful. Volcanic activity would surge as the enhanced heating and deformation of the mantle increased magma production and created new pathways for magma to reach the surface. Earth might enter a period of intense volcanism reminiscent of its early history, with widespread eruptions altering the atmosphere and climate. The tidal heating would not be evenly distributed. It would be strongest in the regions of the crust and mantle that experience the greatest deformation, particularly in the equatorial regions where the tidal bulge is most pronounced. Over time, this could lead to differential heating and deformation of the planet's interior, potentially affecting plate tectonics in complex ways. The enhanced convection the mantle driven by the additional heat source might accelerate continental drift or alter the patterns of subduction and seafloor spreading. Mars in the sky would be a stunning sight. Mars has a diameter of about 6,800 kilometers, roughly twice the diameter of the Moon. At the Moon's orbital distance, Mars would appear roughly twice as large in angular size as the Moon, subtending an angle of about 1 degree. This would make it a dominant feature of the sky, appearing as a large disk that would make the night far brighter. When Mars is full, the color would be distinctly different from the Moon's pale gray. Mars would appear reddish-orange, the characteristic rusty hue caused by iron oxide on its surface. This red planet in our sky would cast a noticeably colored light during its full phase, tinting the night landscape with a warm, eerie glow. The phases of Mars would be dramatic and easily visible. During a full Mars, when Earth is between Mars and the Sun, the red planet will be a brilliant object dominating the night sky, far brighter than the full moon we are accustomed to. During a new Mars, when Mars passes between Earth and Sun, we might witness transits where Mars's disk blocks out a portion of the Sun's light, creating a dramatic darkening visible from the day side of Earth. Unlike solar eclipses caused by the Moon, which appears a near-perfect blocking of the Sun due to the Moon's angular size almost exactly matching the Sun's, Mars would appear twice as large as the Sun's half-degree diameter, creating a different kind of eclipse event where a large circular shadow crosses the Sun's face. The increased tidal braking would cause Earth's rotation to slow much more rapidly than it currently does. Within a few tens of millions of years, Earth could become tidally locked to Mars, meaning one side of Earth would perpetually face Mars while the other side would never see it. This is the same phenomenon that has caused the moon to become tidally locked to Earth, always showing us the same face. If Earth became tidally locked to Mars, one hemisphere would experience continuous daylight as the sun moved around the sky over the course of a year, while the other hemisphere experienced continuous darkness, with Mars hanging motionless in the sky on one side and absent entirely from the other. The climate consequences would be extreme, with one hemisphere baking and the other freezing, and only a narrow band around the terminator potentially maintaining moderate temperatures. However, tidal locking would take considerable time, and before it occurred, the intermediate stages would be significant. As Earth's rotation continued to slow, days would become longer and longer. When days reached 40 or 50 hours in length, atmospheric circulation patterns would be completely reorganized. The difference in solar heating between day and night will become more extreme, driving powerful winds from the heated day side to the cooling night side. These winds will be far stronger than any currently experienced on Earth. Weather patterns will be dominated by these day-night circulation cells, and the familiar patterns of mid-latitude storms and tropical weather systems might be replaced by simpler but more extreme circulation regimes. Let us now escalate further and consider replacing the moon with Venus. Venus has a mass of about 4.8 times 10 to the 24 power kilograms, approximately 82% of Earth mass, or about 67 times the mass of the moon. Venus is nearly Earth's twin in terms of size and mass, though radically different in surface conditions. If Venus were placed at the moon's orbital distance, the tidal forces would increase by a factor of 67. This enters a regime that is no longer merely catastrophic for coastal regions and tectonic stability, but threatens the structural integrity of Earth itself. Tidal forces scale with the mass of the perturbing body, divided by the cube of the distance. With 67 times the moon's mass at the same distance, the tidal force would be 67 times greater. Ocean tides would no longer be measurable in meters, but in hundreds of meters. The entire ocean would be pulled into enormous bulges toward and away from Venus, creating massive traveling waves that would sweep around the planet. These are not ordinary waves, but tidal distortions of the entire ocean basin. Coastal regions will be completely submerged under hundreds of meters of water at high tide, and during low tide, vast expanses of ocean floor will be exposed. The energy dissipated by this movement of water would heat the ocean significantly, potentially raising ocean temperatures enough to alter global climate. The solid Earth tides would reach amplitudes of many tens of meters. The entire crust and mantle would flex dramatically twice per day, and the amount of tidal heating generated would be immense. To put this in perspective, Jupiter's moon Io, which is the most volcanically active body in the solar system, owes its extreme volcanism to tidal heating from Jupiter. Io's tidal heating is so intense that it resurfaces the entire moon through volcanic activity, maintaining a young, crater-free surface. Earth, under the tidal influence of Venus at such close range, would experience heating approaching Io's level. The planet would become volcanically hyperactive. Magma would be generated in vast quantities throughout the mantle, and volcanic eruptions would occur almost continuously across the planet. The surface would be broken by countless new volcanoes, and existing volcanic systems will become far more active. The seismic consequences will be beyond anything in the historical or geological record. Earthquakes of magnitude 8 or higher would occur daily. Magnitude 9 earthquakes would be common. The crust would be in a constant state of deformation, and no structure built by human hands could withstand the continuous shaking. Cities would be impossible to maintain. The landscape itself would be constantly changing as the ground rose and fell, as new faults opened, and as volcanic activity reshaped the surface. The tidal breaking would slow Earth's rotation extremely rapidly. Within a few million years, Earth would become tidally locked to Venus. But long before that happened, the slowing rotation would alter the planet's magnetic field. Earth's magnetic field is generated by convection of molten iron in the outer core, a process that depends on the planet's rotation. As rotation slows, the dynamo mechanism that generates a magnetic field could be disrupted. If Earth's magnetic field weakened significantly or collapsed entirely, the planet would lose its primary shield against the solar wind, the stream of charged particles flowing from the sun. Without this shield, the solar wind would strip away the upper atmosphere over time, as has happened on Mars, which lacks a global magnetic field. Earth could lose an atmosphere on geological timescales, transforming into a barren, airless world. Visually, Venus in the sky would be an overwhelming presence. Venus has a diameter of about 12,100 kilometers, just slightly smaller than Earth's 12,742 kilometers. At the Moon's orbital distance, Venus would appear about 3.5 times larger in angular size than the Moon, subtending an angle of roughly 1.7 degrees. It would appear as a massive, brilliant disk dominating the sky. Unlike Mars, which displays its rusty surface, Venus is perpetually shrouded in thick clouds of sulfuric acid. What we would see would not be the surface, but the cloud tops, which are relatively featureless and yellowish white. The brightness would be extraordinary. Venus will reflect a large fraction of the sunlight that hits it, making full Venus bright enough to cast distinct shadows at night and to be easily visible during the day, appearing as a huge pale disk alongside the sun. The psychological impact of such a massive object in the sky cannot be overstated. It would dominate human consciousness. Ancient cultures would have built their entire cosmologies around such a prominent celestial feature, and modern humans, suddenly presented with this new sky, would feel a profound sense of displacement and awe. The tides alone would force a complete reorganization of human civilization away from coastlines, but the visual presence of Venus would be equally transformative. We must also consider what would happen during eclipses. With Venus nearly 4 times the angular diameter of the Sun, a solar eclipse would be a prolonged, dark event. When Venus passed between Earth and the Sun, the entire Sun would be blocked out, not just barely as with the Moon's eclipses, but completely, with Venus's disk far exceeding the Sun's apparent size. The sky would become dark for an extended period as Venus slowly transited across the Sun, and the amount of sunlight reaching Earth would be dramatically reduced during the transit. Depending on the orbital periods and alignments, these transits could become relatively frequent, causing temporary but significant climate effects each time they occurred. However, we must address a critical question. Could Venus actually orbit stably at the Moon's distance? With 82% of Earth's mass, Venus is not a minor satellite, but a near peer. The center of mass of the Earth-Venus system would lie not deeper than Earth, but much closer to the surface, perhaps just within or even outside Earth's physical radius. This is no longer a planet-moon system, but a binary planet system. Both Earth and Venus would orbit around their common center of mass, or bare center. The stability of such a system depends on many factors, including the initial orbital configuration and the presence of the Sun. The Sun's gravitational perturbations on such a system would be significant, and over time, the orbits might evolve in complex ways. There is a real possibility that the system could be unstable on timescales of millions to tens of millions of years, with the orbits either causing the two planets to drift apart or, more catastrophically, to eventually collide. If Earth and Venus were to gradually spiral inward toward each other due to tidal evolution and loss of orbital energy, the consequences would escalate beyond anything we have discussed so far. As the distance decreased, tidal forces would scale as the inverse cube of the distance, meaning they would increase very rapidly. At half the current Moon distance, tidal forces would be 8 times stronger than at the Moon's distance. At 1/4 the distance, they would be 64 times stronger. Long before the two planets collided, they would be ripped apart by tidal forces exceeding the gravitational self-binding of the planets themselves. This is the Roche limit, the distance within which a celestial body held together only by its own gravity will disintegrate due to tidal forces. For planets as large as Earth and Venus, the Roche limit is quite close, perhaps only 2 to 3 times the radius of the larger body. As the two planets approach this limit, they would begin to disintegrate, with material being pulled off the surfaces and forming streams of debris that would eventually coalesce into a ring system or, over longer periods, reaccrete into new moons or merge into a single, larger planet. The collision of Earth and Venus, should it occur, will be one of the most energetic events possible in planetary science short of interactions with much more massive bodies or stars. The kinetic energy involved in two Earth-sized planets colliding at orbital velocities would be sufficient to completely melt both planets, vaporizing large fractions of their mass. The resulting body would be a molten blob of rock and metal, glowing with heat, surrounded by a vast atmosphere of rock vapor that would eventually cool and condense, raining back down onto the surface. This is similar to what is believed to have happened when Earth collided with a Mars-sized body early in its history, an event that formed the Moon. But a collision between Earth and Venus would be even more energetic, and the resulting body would be a new super-Earth, more massive and larger than either original planet, with all traces of the biosphere, oceans, and atmosphere of the original Earth obliterated and redistributed into a new, alien world. Let us now turn to the gas giants, beginning with Neptune. Neptune has a mass of about 102 times 10 to the 24 power kilograms, roughly 17 times Earth's mass, or about 1,400 times the mass of the Moon. Placing Neptune at the Moon's orbital distance would subject Earth to tidal forces 1,400 times stronger than those from the Moon. This is a regime that enters into the realm of immediate destruction. The tidal forces would exceed the structural strength of Earth's crust and mantle over much of the planet. The solid Earth would be pulled into tidal bulges hundreds of kilometers high. The crust would fracture and separate, and the mantle would flow like a fluid on short time scales. The planet would be torn apart. The Roche limit becomes critically important here. For a rigid body, the Roche limit is approximately 2.5 times the radius of the larger body. Neptune's radius is about 24,600 kilometers, roughly 4 times that of Earth. If Neptune were at the Moon's distance of 384,000 kilometers, this would be only about 15 times Neptune's radius, well within the range where tidal forces could disrupt a smaller body. Earth, being less massive than Neptune, would be subject to tidal forces that exceed its gravitational self-binding. The planet would not remain intact, but would begin to break apart, with material being pulled toward Neptune and spreading into a ring or disk of debris. But let us imagine, for the sake of exploration, that we could somehow stabilize Earth against this disruption, perhaps by considering a somewhat greater distance or by examining the effects before the final disruption occurs. Neptune in the sky would be an astonishing sight. Neptune has a diameter of about 49,500 kilometers, roughly 4 times Earth diameter, or about 14 times the Moon's diameter. At the Moon's distance, Neptune would subtend an angle of about 7 degrees, appearing as a massive disk that would cover a significant portion of the sky, roughly 14 times the angular diameter of the Moon. When full, it would be an overwhelmingly bright object, and its deep blue color, caused by methane in its atmosphere absorbing red light, would cast a blue glow over the night landscape. The visual experience would be surreal and alien. During the night with full Neptune, the landscape would be bathed in blue light, bright enough to read by, bright enough to see colors and details. Shadows would be sharp and distinct. The sky would appear to be divided between the darkness of space and the enormous glowing disk of Neptune, with its bands of clouds and storms visible even to the naked eye. The great dark spot, Neptune's equivalent to Jupiter's great red spot, would be a visible feature, a dark oval moving slowly across the planet's face over the course of its rotation. Since Neptune rotates roughly every 16 hours, observers on Earth would see the planet's features shift and change noticeably from night to night. However, the tidal heating and deformation would make Earth uninhabitable long before humans could enjoy such views. The planet would be in a state of extreme volcanic and seismic activity. The surface would be molten or semi-molten in many regions, and the atmosphere would be choked with volcanic gases and ash. The oceans would boil away as the tidal heating raised global temperatures to unbearable levels. Any complex life would be extinguished rapidly, and even microbial life would struggle to survive, except perhaps in deep subsurface environments where temperatures remain moderate. The tidal locking timescale would be extremely short. Within thousands to millions of years, depending on the details of the energy dissipation, Earth would become tidally locked to Neptune. The rotation would slow to match the orbital period, which, at the Moon's distance, would be about 27 days. But during the transition, as the rotation slowed from 24 hours to hundreds of hours, the planet would experience dramatic changes in atmospheric circulation, ocean currents, and climate. The Coriolis effect would weaken, altering the paths of winds and currents. The day-night temperature difference would increase dramatically, driving powerful winds and creating extreme weather. Eventually, with one side of Earth perpetually facing Neptune and the other side perpetually facing away, the climate would settle into a new equilibrium, but it would be an equilibrium of extremes, with the Neptune-facing side experiencing different conditions than the far side. Uranus, being similar in mass to Neptune at about 14.5 times Earth's mass, would produce similar effects if placed at the Moon's distance. Uranus would appear slightly smaller than Neptune due to its slightly smaller radius of about 25,362 kilometers, but the tidal forces would be comparable. The most notable difference would be Uranus's unique rotational orientation. Uranus rotates on its side, with its axis tilted 98 degrees relative to its orbital plane. This means that as Uranus orbited Earth, we would alternately see its north pole, its equator, and its south pole facing us, creating a bizarre pattern of illumination and appearance. The planet would appear to roll around Earth rather than rotating conventionally. This would create strange visual effects, with the bands and features of Uranus's atmosphere appearing to rotate in unusual ways from our perspective. Now we come to the true giants, Jupiter and Saturn. Jupiter has a mass of approximately 1.9 times 10 to the 27 power kilograms, about 318 times Earth's mass, or roughly 26,000 times the mass of the Moon. Placing Jupiter at the Moon's orbital distance would subject Earth to tidal forces 26,000 times stronger than the Moon's. Earth would be well within Jupiter's Roche limit and would be instantly torn to shreds. There would be no gradual process of increasing volcanic activity or seismic events. The planet would simply disintegrate into a stream of debris that would spread around Jupiter in a ring, much like the rings of Saturn, but composed of material that once formed Earth. The Roche limit for Earth in Jupiter's gravitational field can be calculated using the formula for a rigid body, which gives a distance of about 2.5 times Jupiter's radius times the cube root of the ratio of Jupiter's density to Earth's density. Jupiter's radius is about 71,400 kilometers, and its average density is about 1.3 grams per cubic centimeter compared to Earth's 5.5 grams per cubic centimeter. The Roche limit is therefore approximately 119,000 kilometers from Jupiter's center, or about 47,000 kilometers above Jupiter's cloud tops. The Moon's orbital distance is 384,000 kilometers, which is comfortably outside this limit, but Earth, being much larger and more massive than typical moons, would experience tidal stresses that, combined with its own structural limitations, would lead to breakup. But let's again imagine that we could somehow prevent this immediate disintegration, perhaps by placing Jupiter at a greater distance or by considering the effects at the edge of stability. Jupiter in the sky would be an unimaginable sight. Jupiter's diameter is about 143,000 kilometers, roughly 11 times Earth's diameter, or about 40 times the Moon's diameter. At the Moon's distance, Jupiter would subtend an angle of about 21 degrees, appearing as an enormous disk covering roughly 1/16 of the entire sky from horizon to zenith. When full, Jupiter would be so bright that the night would be nearly as bright as day, though with a different quality of light. Jupiter's reflected sunlight would illuminate the Earth's surface with an intensity far exceeding that of the full moon. The visual features of Jupiter would be spectacular. The bands of clouds, the zones and belts created by Jupiter's powerful atmospheric circulation, would be easily visible to the naked eye, stretching across the enormous disk. The Great Red Spot, a storm system larger than Earth that has persisted for at least hundreds of years, would be a prominent feature, appearing as a large reddish oval on the planet's face. As Jupiter rotates every 10 hours, these features would move noticeably across the disk over the course of night, giving the eerie impression of a living, changing giant in the sky. The moons of Jupiter, Io, Europa, Ganymede, and Callisto, would also be visible, appearing as bright dots moving around the planet's disk. They would transit across Jupiter's face, casting shadows onto the cloud tops that would be visible from Earth. In turn, these moons themselves would be dramatically affected by having Earth so close, and the entire Jovian system would be disrupted. The tidal forces, even at a distance that prevented Earth's immediate destruction, would be devastating. Earth's surface would heave and buckle continuously. The mantle would be in a state of vigorous convection driven by extreme tidal heating, generating temperatures throughout the interior that would melt rock. The surface would be a chaotic landscape of volcanoes, lava flows, and fractured crust, constantly reshaped by tectonic activity and impacts from debris. The atmosphere would be thick with ash and volcanic gases, blocking sunlight and creating a runaway greenhouse effect. The oceans would have boiled away, their water dissociated into hydrogen and oxygen by ultraviolet radiation, with the hydrogen escaping to space and the oxygen reacting with surface rocks. Earth would resemble Io, a world of fire and brimstone, utterly inimical to life. The gravitational interaction between Earth and Jupiter would also transfer enormous amounts of angular momentum. Jupiter's gravitational field would exert torque on Earth's tidal bulge, but because Jupiter is so much more massive than Earth, the effect on Jupiter will be minimal, while the effect on Earth will be extreme. Earth's rotation would slow rapidly, and the planet would become tidally locked to Jupiter on timescales of perhaps only thousands of years. The transfer of energy would also cause Earth's orbit around Jupiter to evolve, potentially causing the orbit to decay inward toward Jupiter or to be perturbed outward, depending on the complex interplay of tidal forces, orbital resonances, and the influence of the Sun. We must also consider the broader context. If Jupiter were somehow in Earth's orbit around the Sun, the entire solar system would be affected. Jupiter's massive gravitational field would perturb the orbits of all the other planets, potentially destabilizing the entire system. Mars's orbit would be significantly affected, possibly leading to ejection from the solar system or collision with another planet. Venus's orbit would also be perturbed. Even the distant outer planets would feel Jupiter's influence more strongly if it were repositioned. The asteroid belt, held in place by Jupiter's gravity in its current location, would be completely disrupted if Jupiter moved to Earth's position. Asteroids would be scattered throughout the inner solar system, leading to a dramatic increase in impacts on all the terrestrial planets. Saturn, with mass of about 95 times Earth's mass and a radius of about 58,232 kilometers, would produce effects similar to Jupiter, but somewhat less extreme due to its lower mass. Saturn would still be well beyond Earth's ability to withstand at the Moon's distance, and the planet would be torn apart by tidal forces. Saturn's magnificent ring system, however, would be an unforgettable addition to the view. If Saturn were in place of the Moon, its rings, extending far beyond the planet itself, would be visible as a broad, bright band stretching across the sky, tilted at an angle depending on Saturn's orbital orientation. The rings would shine brilliantly when illuminated by the sun, and their complex structure of gaps and divisions will be visible with even modest optical aid. The shadow of the rings on Saturn's globe will be a prominent feature, as with the shadow of Saturn on its rings. As Saturn orbited Earth, the angle at which we viewed the rings would change slightly over time due to orbital mechanics, creating a slowly varying spectacle. The tidal heating from Saturn would be intense, but not quite as extreme as from Jupiter. Earth would still become volcanically hyperactive, with widespread melting of the crust and mantle, boiling of the oceans, and loss of the atmosphere. The planet would become a molten hell, tidally locked to Saturn, with its surface constantly reshaped by volcanic activity and tidal deformation. The rotation would slow to match the orbital period, and the magnetic field would likely collapse, exposing the planet to the full force of the solar wind. Now let us shift our perspective and consider not just the immediate physical effects, but the longer-term orbital evolution and stability of these scenarios. When two bodies orbit each other, they exchange energy and angular momentum through tidal interactions. The specifics depend on the rotation rates of the bodies, their orbital period, and the distribution of mass within each body. For the Earth-Moon system, the Moon is already tidally locked to Earth, always showing the same face. Earth is not yet tidally locked to the Moon, but the tidal interaction is gradually slowing Earth's rotation and pushing the Moon farther away. Eventually, billions of years in the future, Earth would become tidally locked to the Moon, and the system would reach a state of minimum energy where both bodies always show the same face to each other, and the orbital period equals both rotation periods. If we replace the Moon with a more massive planet, the time scale for tidal locking would be much shorter because the strength of the tidal interaction scales with the mass of the perturbing body. A more massive object produces stronger tides, which dissipate more energy and transfer angular momentum more efficiently. For Venus at the Moon's distance, the tidal locking timescale might be on the order of millions of years. For Jupiter, it might be only thousands of years. But tidal locking is not necessarily the end of the story. The system would still be subject to external perturbations, particularly from the Sun. The Sun's gravity would perturb the orbits, causing them to evolve over time. For a binary planet system like Earth-Venus, the Sun's perturbations could cause the orbit to become eccentric, bringing the two planets closer together during part of each orbit and farther apart during other parts. This eccentricity could pump additional energy into the system through tidal flexing during the closest approaches, leading to even more heating and potentially destabilizing the system entirely. In the case of the gas giants, the scenario is even more complex. A gas giant at the moon's distance from Earth would dominate the gravitational environment. Earth would effectively become a moon of the gas giant, and the primary orbit around the sun would be that of the gas giant with Earth as a satellite. The stability of Earth's orbit around the gas giant would depend on whether it remained within the gas giant's Hill sphere, the region where the gas giant's gravity dominates over the sun's. Jupiter's Hill sphere, if Jupiter were in Earth's current orbit around the sun, would extend to about 53 million kilometers, far larger than the moon's current orbital distance of 384,000 kilometers. So Earth could stably orbit Jupiter in that configuration. However, the sun's tidal perturbations on Earth's orbit around Jupiter would cause the orbit to evolve over long timescales, potentially leading to changes in eccentricity and inclination. We must also consider the effect on Earth's orbit around the sun itself. Currently, Earth orbits the sun in a near-circular orbit at a distance of about 150 million kilometers. If a massive planet like Jupiter were placed very close to Earth, the center of mass of the Earth-Jupiter system would be much closer to Jupiter than to Earth, and the system as a whole would orbit the sun with that center of mass following an elliptical path. Earth's motion would then be a combination of its orbit around Jupiter and the orbit of the Earth-Jupiter barycenter around the sun. This is similar to how Pluto and Charon, being a binary system, orbit the sun with their common center of mass following the orbital path. For Earth and Jupiter, the barycenter will be only about 747,000 kilometers from Jupiter's center, which is inside Jupiter itself since Jupiter's radius is about 71,000 kilometers. So Jupiter would barely wobble, while Earth would orbit around a point just outside Jupiter's cloud tops. Another critical consideration is the effect of tidal heating on the long-term habitability of Earth. Tidal heating is a double-edged sword. On one hand, it can provide an internal heat source that drives geological activity, potentially maintaining conditions suitable for life. Jupiter's moon Europa, for example, is kept warm by tidal heating from Jupiter, maintaining a subsurface ocean beneath its icy crust despite being far from the sun. On the other hand, excessive tidal heating can turn a world into a volcanic nightmare like Io, rendering it completely uninhabitable. For Earth, the current level of tidal heating from a moon is very modest and does not significantly affect the planet's thermal budget. Earth's internal heat is dominated by radioactive decay of elements like uranium, thorium, and potassium in the mantle and crust, along with residual heat from the planet's formation. The moon's tidal heating contribution is negligible in comparison. However, if Earth were subjected to tidal heating from a planet like Venus, Mars, or especially a gas giant, the tidal contribution could equal or exceed the radioactive heating, fundamentally altering the planet's thermal evolution. The mantle will be hotter and more vigorously convecting, which could increase the rate of plate tectonics, leading to faster continental drift and more rapid recycling of the crust. Volcanism would be more widespread and vigorous. Over geological time, this could lead to a faster loss of volatiles from the interior, altering the composition of the atmosphere and oceans. Carbon dioxide, water vapor, and other gases would be outgassed more rapidly, potentially creating a thicker, hotter atmosphere. If the tidal heating were extreme, the planet could enter a runaway greenhouse state similar to Venus, where surface temperatures become hot enough to vaporize water, preventing it from condensing as rain and allowing it to be lost to space. Let us also consider the perspective of an observer on Earth's surface in these scenarios. Imagine standing on a beach at night with Mars hanging in the sky, twice the size of the moon we know, glowing red like a second, smaller sun. The tides would be so extreme that over the course of a few hours, you would see the water recede hundreds of meters, exposing the seafloor, and then rush back in with tremendous force, flooding areas far inland. The ground beneath your feet would be in constant motion, rising and falling by meters as a solid earth tide passed beneath you. Earthquakes would rumble through the ground frequently, and the horizon might glow with the light of distant volcanic eruptions, so numerous that the smoke and ash would create perpetual twilight during the day. The air would smell of sulfur and ash. The climate would be chaotic, with extreme weather driven by the disrupted atmospheric circulation and the heat from volcanic activity. This would not be a world that humans could inhabit without extraordinary technology and adaptation. Now imagine the same scene with Jupiter in the sky. Jupiter would be so large that it would dominate your entire field of view if you looked upward. It would not be merely an object in the sky, but a sky-filling presence, a ceiling of swirling clouds and storms stretching from horizon to horizon in some parts of its orbit. The bands of Jupiter would be like geographic features in themselves, immense zones of different colors and textures that you could watch evolve and change over the course of nights. The Great Red Spot would be a permanent fixture, a storm so large it could swallow Earth whole, drifting slowly across the face of the giant. The moons of Jupiter would be bright points of light, moving visibly from hour to hour, and you might even see volcanic eruptions on Io as bright flashes of light when that moon was on the side facing Earth. The light from Jupiter would be so intense that the night would be nearly as bright as an overcast day. Plants, if any survived, might attempt to photosynthesize using Jupiter's reflected light. Nocturnal animals would be confused by the brightness, and the traditional concepts of day and night would be blurred. But all of this is academic in the face of the tidal destruction. No observer would survive to witness these sights. The planet would be uninhabitable, its surface molten, its atmosphere stripped away or choked with volcanic gases, its water lost to space. The only refuge might be deep underground, in caverns insulated from the surface chaos, where temperatures remain moderate and the rock overhead shielded against radiation. Even there, the constant seismic activity would make survival precarious. We should also examine the effect on the moon's own structure if it were replaced by a planet with a different internal composition. The moon is a differentiated body with a small iron core, a mantle of silicate rock, and a crust that is also silicate-rich but less dense than the mantle. Its interior is relatively cold and inactive, with no current volcanic activity and no magnetic field. The planets, by contrast, have much more complex and active interiors. Mars has a partially molten core and shows evidence of past volcanic activity, though it is currently much less active than Earth. Venus has a hot interior and is likely still geologically active, though its volcanism is hidden beneath its thick atmosphere. The gas giants have no solid surface at all, only layers of gas and liquid surrounding small cores of rock and ice. If Mars replaced the moon, Mars itself will be subject to tidal forces from Earth. These forces will be modest compared to what Earth would experience, but they would still have effects. Mars would experience solid body tides that would flex its interior, generating some tidal heating. This could potentially reactivate Mars's dormant volcanic systems, causing new eruptions and lava flows. Mars's atmosphere, which is currently very thin, might be partially stripped away by interactions with Earth's magnetic field and the solar wind, or it might be enhanced by outgassing from renewed volcanic activity. Mars's moons Phobos and Deimos would be perturbed by Earth's gravitational influence and might be ejected from the system or pulled into Mars, causing impacts. If Venus replaced the moon, Venus would also experience tidal forces from Earth, though Venus is massive enough that the effect on its interior would be relatively minor. However, Venus's thick atmosphere will be subject to gravitational interactions with Earth. The two atmospheres might even interact if the planets were close enough. Though at the moon's distance, they would still be far too separated for direct atmospheric contact. Venus's slow rotation, currently retrograde with a period of 243 Earth days, would be affected by Earth's tidal forces. Over time, Venus might become tidally locked to Earth as well, with both planets eventually showing the same face to each other perpetually. The gas giants, being composed primarily of hydrogen and helium with no solid surface, would not experience tidal stresses in the same way rocky planets do. However, their deep atmospheres and fluid interiors will be subject to tidal deformations, creating bulges in the density distribution and potentially enhancing internal heat generation through friction. This could lead to more vigorous atmospheric dynamics and more intense storm systems. Jupiter's Great Red Spot might become even larger and more powerful if Jupiter were subjected to strong tidal forces from another massive body at close range. Let us now turn to a different aspect of this scenario: the gravitational perturbations on other objects in the solar system. The moon currently has a small but measurable effect on the orbits of Earth-approaching asteroids and comets. Its gravitational field can slightly deflect these objects, sometimes enough to change whether they will impact Earth or miss it. If the moon were replaced by a much more massive planet, these gravitational perturbations would be much stronger. Asteroids that might otherwise have passed harmlessly by Earth could be deflected into collision courses, or vice versa. The overall flux of impacts on Earth might increase or decrease depending on the specific configuration and how the new planet's gravity reshaped the population of near-Earth objects. Similarly, artificial satellites orbiting Earth would be affected. Currently, satellites in low Earth orbit are primarily influenced by Earth's gravity, with small perturbations on the moon, the sun, and the non-spherical shape of Earth. If a massive planet replaced the moon, satellites would experience much stronger perturbations that would alter their orbits significantly over time. Maintaining satellites in stable orbits would require more frequent corrections, and some orbits that are currently stable might become unstable. Geostationary orbit, where satellites orbit at an altitude that keeps them fixed above a point on Earth's equator, will be particularly affected. The gravitational pull of a massive nearby planet would perturb geostationary satellites out of their positions, potentially rendering this type of orbit unusable. The Lagrange points of the Earth-Moon system would also be completely reconfigured. Currently, the 5 Lagrange points of the Earth-Moon system are locations where a small object can maintain a stable or semi-stable position relative to the Earth and Moon. The L4 and L5 points, located 60 degrees ahead of and behind the Moon in its orbit, are stable and could in principle host satellites or even natural objects for long periods. If the Moon were replaced by a more massive planet, the Lagrange points would shift to new locations, and their stability properties would change. For a very massive planet, the L1 point, located between Earth and the planet, could become a significant gravitational feature, potentially trapping dust and small debris in a region of space between the two bodies. Another fascinating aspect to consider is the effect on space exploration and human spaceflight. Currently, the Moon is a major target for exploration and a potential site for future human settlement. Its proximity makes it accessible with relatively modest rocket technology, and its low gravity makes landing and taking off feasible. If the Moon were replaced by a planet, the nature of space exploration from Earth would change dramatically. Mars at the Moon's distance would be more difficult to land on due to its higher gravity, but it might offer more resources in terms of thicker atmosphere and potentially more water ice. Venus at that distance would be completely inaccessible due to its extreme surface conditions and thick, corrosive atmosphere. The gas giants would be impossible to land on, having no solid surface, though their moons would become new exploration targets at closer range than their current positions in the outer solar system. If Jupiter were at the Moon's distance, Jupiter's large moons, Io, Europa, Ganymede, and Callisto, would be much closer to Earth than they currently are. These moons are fascinating worlds in their own right. Europa is believed to have a subsurface ocean that might harbor life. Ganymede is the largest moon in the solar system and has its own magnetic field. Io is the most volcanically active body in the solar system. Callisto is heavily cratered and ancient. Having these moons so close would make them prime targets for exploration, and missions to them would take days or weeks rather than years. However, the radiation environment near Jupiter is extremely hazardous. Jupiter has a powerful magnetic field that traps charged particles in radiation belts far more intense than Earth's Van Allen belts. Spacecraft and astronauts venturing close to Jupiter would be exposed to lethal doses of radiation, making exploration challenging. Let us also explore the cultural and mythological implications. Human cultures have been shaped by the Moon's presence for all of recorded history, and likely for hundreds of thousands of years before that. The moon cycles have been used to measure time, giving rise to the concept of the month. Many calendars are based on lunar cycles. Religious festivals, agricultural practices, and cultural traditions are tied to the moon's phases. The full moon and new moon have symbolic significance in countless mythologies. If the moon were suddenly replaced by a planet, these deeply ingrained cultural patterns would be disrupted. New myths would have to be created to explain the new object in the sky. The length of a month might change if the orbital period changed. The appearance of the night sky would be so different that star navigation would have to be relearned. Different planets would carry different symbolic weight. Mars, with its red color, has long been associated with war and aggression in human mythology, named after the Roman god of war. If Mars hung in our sky, it might reinforce or alter these associations. Venus, named after the Roman goddess of love, appears as a brilliant white or yellowish object when seen from Earth in its current orbit as the morning or evening star. If Venus were in the sky as a massive disk, it might be seen as a goddess figure made manifest, a maternal or feminine presence watching over the Earth. Jupiter, king of the gods in Roman mythology, would certainly seem regal and imposing as a sky-filling giant. Neptune, god of the sea, would bring its blue color and associations with water and mystery. We should also consider the perspective from the replaced planet's original position in the solar system. If Mars were moved from its current orbit to Earth's orbit to replace the Moon, the solar system would have a gap where Mars used to be. The asteroid belt, which lies between Mars and Jupiter, would be affected by the loss of Mars's gravitational influence. Some asteroids might be perturbed into new orbits, and the structure of the asteroid belt would evolve over time. Conversely, if Jupiter were moved to Earth's orbit, the outer solar system would be dramatically altered. Saturn, Uranus, and Neptune would no longer have Jupiter's gravitational influence shaping their orbits. The asteroid belt would be completely disrupted without Jupiter acting as a gravitational shepherd. Many asteroids would be scattered inward toward the Sun, or outward into the outer solar system, or even out of the solar system entirely. The stability of the entire solar system would be questionable. In fact, one of the most profound aspects of our question is that it reveals just how finely tuned the solar system is. The planets orbit in a specific configuration that has been stable for billions of years. This stability arises from the fact that the planets are spaced out in a way that avoids strong resonances and perturbations that would destabilize their orbits. The planets are also in orbits that keep them well separated, preventing close encounters and collisions. If we were to arbitrarily move a planet from its current location to replace the Moon, we would be disrupting this delicate balance, and the consequences would ripple throughout the entire system. This is not just a local change affecting only Earth, but a change that affects every body in the solar system to some degree. The question of what would happen if the Moon were replaced by a planet also invites us to think about planetary formation and the processes that shape solar systems. The Moon is thought to have formed from debris ejected when Earth collided with a Mars-sized protoplanet in the early solar system, an event called a giant impact. This collision was one of many violent events during the period of planetary formation, when the solar system was filled with planetesimals and protoplanets, colliding and merging to form the planets we see today. The fact that Earth ended up with such a large moon relative to its size is somewhat unusual. Most planets either have no moons, many small moons, or few medium-sized moons. Earth's situation of having one large moon is special, and has had significant consequences for our planet's evolution. If planetary formation had gone differently, Earth might have ended up in a binary system with another planet of similar size, rather than having a single large moon. In such a scenario, the two planets would orbit their common center mass, and both would experience tidal effects from the other. The evolution of such a system would depend on many factors, including the initial separation and orbital eccentricity, the rotation rates of the two planets, and the internal structure and composition of each planet. Some binary planet systems might be stable and long-lived, while others might evolve toward merger or separation. In our own solar system, Pluto and Charon are an example of a binary system, though at a much smaller scale. Charon is about half the diameter of Pluto and has about 1/8 of Pluto's mass. The two bodies are tidally locked to each other, always showing the same face, and they orbit their common center of mass, which lies outside Pluto's surface. This system is stable and has existed for billions of years. If Earth were in a similar configuration with another planet, the dynamics would be analogous but on a much larger scale, with much greater consequences due to the larger masses and energies involved. Let us now consider what would happen to life on Earth in these scenarios. Life on Earth has evolved under the specific conditions provided by our planet's environment, including the presence of the Moon. The Moon stabilizes Earth's axial tilt, which provides stable seasons. The Moon creates tides, which are thought to play a role in the origin of life by creating intertidal zones where organic molecules can be concentrated and undergo chemical reactions. The tides also help mix nutrients in the oceans and create diverse habitats along coastlines. The length of the day, which has been slowed by the moon's tidal breaking, affects biological rhythms and has influenced the evolution of many organisms. If the moon were suddenly replaced by a planet, and if Earth were not immediately destroyed by tidal forces, life would face catastrophic challenges. The extreme tides would inundate coastal areas and destroy intertidal ecosystems. The increased volcanic activity would release vast amounts of sulfur dioxide and ash into the atmosphere, blocking sunlight and causing global cooling, a scenario similar to a volcanic winter or impact winter. This cooling could last for years or decades, long enough to cause widespread extinction of photosynthetic organisms, which form the base of most food chains. Herbivores dependent on plants would starve, and carnivores dependent on herbivores would follow. Oceanic food chains, dependent on phytoplankton that requires sunlight, would also collapse. The increased seismic activity would destroy terrestrial habitats, and the continuous ground motion would make it difficult for plants to maintain root systems or for animals to build stable shelters. The rapid changes in climate and day length as Earth's rotation slowed would disrupt biological rhythms and reproductive cycles. Many species have behaviors and physiologies tuned to the current 24-hour day-night cycle, such as circadian rhythms that regulate sleep metabolism and reproduction. If the day length changed to 48 hours or 72 hours, these organisms would face severe stress. Marine life will be particularly affected by the extreme tides. Many marine organisms, especially those in coastal and shallow water environments, are adapted to the current tidal regime. Extreme tides would create much more violent water movement, making it difficult for sessile organisms like corals and oysters to survive. Fish and other mobile marine animals would have to cope with rapidly changing water levels and strong currents. The increased turbidity from sediment stirred up by the tides and from volcanic ash falling into the ocean would reduce light penetration, harming photosynthetic organisms. Deep-sea life might fare better in the short term, as the deep ocean is insulated from many surface disturbances. However, the long-term effect of changes in ocean circulation, temperature, and chemistry would eventually reach the deep sea. If the oceans boiled away due to extreme tidal heating, then even deep-sea life would be exterminated. The only possible refuges for life would be deep in the Earth's crust, in environments where microorganisms live independently of surface conditions, sustained by chemical energy from reactions between rocks and water. These deep biosphere organisms might survive, but complex multicellular life would almost certainly be wiped out. Over longer timescales, if conditions stabilized, life might reemerge and evolve to adapt to the new environment. Evolution is a powerful force, and life has shown remarkable resilience in the face of past catastrophes. However, the new conditions would be so different that the resulting biosphere would bear little resemblance to the one that existed before. If Earth became tidally locked, with one hemisphere perpetually facing the new planet and the other perpetually facing away, life would have to adapt to either perpetual light or perpetual darkness on opposite sides of the planet, with only a narrow twilight zone at the terminator offering moderate conditions. Organisms might evolve to migrate around the twilight zone, following the habitable conditions, or they might specialize to survive in extreme conditions of the perpetual day side or night side. An interesting comparison can be made to exoplanets that orbit close to their stars and are tidally locked. Many of the exoplanets discovered around red dwarf stars are thought to be tidally locked because red dwarfs are cool and dim, requiring planets to orbit very close to receive enough heat, and at such close distances tidal locking occurs rapidly. Scientists studying the habitability of these tidally locked exoplanets consider the challenges they pose for life, including the extreme temperature differences between the day side and night side, the potential for atmospheric collapse if gases freeze out on the night side, and the possibility of a habitable zone only in the twilight region. Earth, if tidally locked to a planet in place of moon, would face similar challenges. Now let us take a step back and consider the sheer improbability of such scenarios from a physical standpoint. Moving a planet from its current orbit to replace the moon would require enormous amounts of energy and would violate the principle of conservation of angular momentum, unless that angular momentum were transferred elsewhere. In a natural scenario, there is no plausible mechanism by which a planet could end up in such a close orbit around Earth. Planetary migration, which does occur in some planetary systems, typically involves interactions over millions of years and usually results in planets moving inward or outward within the system's overall structure, not being captured by another planet. Capture of a rogue planet into orbit around Earth is theoretically possible, but extremely unlikely. For a planet to be captured, it would have to approach Earth with just the right velocity and angle, and there would have to be a mechanism to dissipate enough energy to prevent the planet from escaping after the encounter. In a two-body interaction, conservation of energy and momentum typically result in the incoming object either colliding or slinging past and escaping. A third body or some dissipated process is usually required for capture. In the early solar system, when there were many protoplanets and planetesimals, such chaotic interactions were more common, and captures and collisions shaped the planets. But today, the solar system is much more stable, and such events are extraordinarily rare. However, the purpose of our exploration is not to determine how such a scenario might come about, but rather to explore the consequences if it did. This is a thought experiment, a way to understand planetary physics, orbital mechanics, and the role of the Moon in Earth's system by imagining extreme variations. By considering what would happen if the Moon were replaced by different planets, we gain insight into forces and processes that govern celestial bodies and the conditions necessary for a planet to support life. One final scenario worth considering is the replacement of the Moon with a planet that is not from our solar system, but is instead a hypothetical planet with specific properties. For example, imagine a planet with the same mass as Earth, but much denser, made entirely of iron or some other heavy element. Such a planet would be smaller than Earth despite having the same mass. If placed at the Moon's distance, it would produce the same tidal forces as an Earth-mass planet, but would appear smaller in the sky. Conversely, imagine a planet with the same size as Earth but much less dense, perhaps a puffy gas giant with a large radius but low mass. Such a planet would produce weaker tidal forces, but would appear large in the sky, creating a different balance of visual impact versus physical effect. We could also imagine a planet with extreme properties, such as a very rapid rotation that creates a pronounced equatorial bulge, or a planet with a powerful magnetic field that creates intense auroras visible from Earth, or a planet with a highly reflective atmosphere that makes it exceptionally bright in the sky. Each of these variations would create different experiences and consequences, illustrating the diversity of possible planetary characteristics and the ways in which those characteristics influence interactions with other bodies. Another interesting thought is what would happen if the planet replacing the Moon had its own moon. For instance, if Mars replaced the Moon, Mars's two small moons, Phobos and Deimos, would come along with it. These moons are tiny, only a few kilometers across, but they would be visible from Earth as faint points of light near Mars, orbiting the red planet every few hours to a day. Observers on Earth would see a miniature planetary system in the sky, with Mars and its moons performing a gravitational dance. The presence of these moons would add to the visual complexity and wonder of the spectacle, though their physical effects on Earth would be negligible given their tiny masses. If Jupiter replaced the Moon, Jupiter's four large moons, Io, Europa, Ganymede, and Callisto, would be prominent features. These moons range in size from slightly smaller than our Moon to larger than the planet Mercury. From Earth, they would appear as bright disks or points of light, and their motions would be easily observable over the course of hours and days. Io's intense volcanic activity might even be visible as it erupts, ejecting material into space. Europa's smooth, icy surface will reflect sunlight brilliantly. Ganymede, the largest moon in the solar system, would be an impressive sight. Callisto, heavily cratered and ancient, would appear more like our Moon in texture. The complex choreography of these moons as they orbited Jupiter, transited its disk, and cast shadows would provide endless fascination for observers. We should also consider the effect of the new planet's gravity on Earth's shape. Currently, Earth is not a perfect sphere but an oblate spheroid, slightly flattened at the poles and bulging at the equator due to its rotation. The centrifugal force from rotation causes material to be thrown outward at the equator, creating the bulge. The Moon's gravity also creates a permanent tidal bulge, though this is smaller than the rotational bulge. If a much more massive planet replaced the Moon, the tidal bulge would become much larger, and Earth's shape would be noticeably deformed. Over time, As Earth's rotation slowed due to tidal braking, the rotational bulge would decrease, while the tidal bulge would remain or even increase as the planet's gravity continued to pull on Earth. Eventually, if Earth became tidally locked, the rotational bulge would disappear entirely, and Earth's shape would be dominated by the tidal deformation, creating a permanent elongation toward and away from the planet. This deformation would have implications for Earth's internal structure. The mantle and core would also be deformed, and the redistribution of mass could affect the planet's moment of inertia, its gravitational field, and its rotational dynamics. The stress from the deformation could create faults and fractures in the crust, leading to increased seismic activity. Over geological time, the planet might adjust its shape through plastic deformation and flow of the mantle, but this process would be slow, and the continuous tidal forces would maintain a state of ongoing deformation and stress. Let us now turn to a more philosophical consideration. The question of what would happen if the moon were replaced by a planet is, at its heart, a question about contingency and necessity in the universe. Our existence as humans on Earth is a result of a long chain of events, each of which might have turned out differently. The formation of the moon through the giant impact was a contingent event. It might not have happened, or it might have happened differently, resulting in no moon or multiple moons or a different moon. If the moon had not formed, or if it had been very different, Earth's evolution would have been different, and the conditions that allowed complex life to arise might not have existed. We might not be here to ask these questions. Replacing the moon with a planet in our thought experiment is a way of exploring alternative histories, other paths that Earth's evolution might have taken under different initial conditions. It highlights the specificity and seeming fragility of the conditions that led to us. Yet it also reveals the underlying physical laws and processes that govern all planets and moons, laws that are universal and necessary. Whether the moon is replaced by Mars or Venus or Jupiter, the same fundamental physics applies. Gravity, tides, energy, momentum, heat, pressure, force, motion. These principles are unchanging, and they dictate the consequences in each scenario with mathematical precision. This interplay between contingency and necessity is a central theme in both planetary science and the broader study of the universe. The specific arrangement of planets in our solar system is contingent, the result of the particular conditions during the solar system's formation. But the processes that shape that arrangement, gravitational collapse, accretion, collision, migration, resonance, are necessary consequences of physical law. Understanding both aspects is essential to fully comprehend not just our own solar system, but the countless other planetary systems that exist around other stars. The question also invites us to appreciate the moon itself. By imagining its replacement by planets of various types, we come to see the moon more clearly for what it is, a companion that has shaped our world in countless ways, from the tides that mix the oceans to the stability of our seasons, from the length of our day to protection from certain impacts, from the subject of poetry and art to a target for exploration and discovery. The moon is not a given. It is a specific, unique body with its own history and characteristics, and our world will be vastly different without it or with something else in its place. As we consider the various scenarios, we can also reflect on the future. In a few billion years, the sun will evolve into a red giant, expanding and engulfing the inner planets, likely including Earth. Long before that, perhaps in a billion years, the sun's increasing luminosity will cause Earth's oceans to evaporate, creating a runaway greenhouse effect that will make the planet uninhabitable. The moon will still be slowly receding from Earth, and in the far future, if Earth survives long enough, the two bodies might become fully tidally locked to each other, orbiting their common center of mass with their same faces forever pointed toward each other. But before any of that, humanity may venture into space, establishing settlements on other worlds. And the moon may become one of those worlds, a new home for humans, and a stepping stone to the rest of the solar system. If we ever develop the technology to move planets or to manipulate gravity on planetary scales, we would have to be extraordinarily careful. The thought experiment we have explored shows that seemingly simple changes, like replacing one celestial body with another, can have cascading consequences that affect entire planetary systems. Any attempt to engineer planetary systems would require a deep understanding of orbital mechanics, tidal forces, long-term stability, and the myriad ways in which celestial bodies interact. The universe is not forgiving of mistakes at this scale. A miscalculation could lead to collisions, ejections, or the destruction of habitable worlds. Let us also briefly consider what would happen from the perspective of an outside observer, someone watching the solar system from a distant star. If Earth and the Moon were suddenly replaced by Earth and Mars, or Earth and Venus, or Earth and Jupiter, this observer would see a change in the system's configuration. If they were monitoring the solar system with precise instruments, they might detect changes in the gravitational field, changes in the orbits of other planets, and changes in the light reflected from the bodies. If Jupiter were moved to Earth's orbit, its brightness would increase dramatically as seen from outside the solar system, because it would be much closer to the sun and thus more brightly illuminated. It would also appear larger and might transit across the face of the sun from certain viewing angles, creating a detectable dip in the sun's brightness, similar to how we detect exoplanets through the transit method. This outside observer might wonder what caused such a dramatic rearrangement. If they were able to examine the system in detail, they might see the signs of instability and evolution, the evidence of tidal disruption and orbital decay, the moons being perturbed or ejected, the asteroids being scattered. They might conclude that the system had undergone a catastrophic event or was in the process of reconfiguring itself after a major disturbance. They might see Earth as a doomed world, caught in a death spiral toward a massive planet, or already being torn apart by tidal forces. From their perspective, the system would be fascinating but tragic, a cautionary tale about the importance of orbital stability. Returning to Earth's perspective, we can think about how different human history might have been if the Moon had been replaced by a planet long before humans evolved. If Mars had been in the sky instead of the Moon, and if Earth had somehow remained habitable, the ancient civilizations that arose might have developed different mythologies, different calendars, different understandings of the cosmos. The red planet hanging in the sky, large and imposing, might have been seen as a god of wars in our own mythology, but more immediate and present. Temples might have been built to align with Mars's position. Festivals might have celebrated Mars's phases. The Babylonians, Greeks, and Mayans, who were keen astronomers, might have developed different astronomical models to explain Mars's motion as it orbited Earth. If Venus had been in the sky, its brilliant white disk might have been associated with purity, beauty, or a mother goddess. Its phases would have been obvious and dramatic, unlike the subtle phases of Venus as seen from Earth in its current orbit, where it appears only as a bright point of morning or evening star whose phases require a telescope to see clearly. A Venus and Earth sky as a large disk would show crescents, gibbous phases, and full phases plainly visible to naked eye, and these phases would have been incorporated into timekeeping and ritual. If Jupiter had been in the sky, it would have been the dominant feature of human cosmology. Its sheer size and brightness would have made it impossible to ignore, and it might have been seen as the chief deity, the ruler of the heavens, in a much more literal sense than Jupiter was viewed by the Romans. The motion of Jupiter's moons would have been observable without telescopes, and ancient astronomers might have deduced a heliocentric model of the solar system earlier, recognizing that just as the Galilean moons orbit Jupiter, the planets orbit the sun. Galileo's observations of Jupiter's moons in the 17th century were crucial in supporting the heliocentric model. Imagine if such observations had been possible thousands of years earlier with the naked eye. Let's consider one more aspect: the effect on tides in the atmospheres of both Earth and the replacing planet. We have discussed ocean tides and solid Earth tides, but atmospheres also experience tides. Atmospheric tides are oscillations in atmospheric pressure, temperature, and wind driven by gravitational forces and solar heating. On Earth, atmospheric tides are relatively subtle and are mainly driven by solar heating rather than the Moon's gravity, though the Moon does contribute a small gravitational component. If a massive planet replaced the Moon, atmospheric tides would become much stronger. The atmosphere will be pulled toward the planet, creating a bulge in the density and pressure distribution. This could lead to enhanced atmospheric circulation, with strong winds flowing between regions of high and low pressure created by the tidal distortion. For the replacing planet, if it had an atmosphere, it would also experience tides from Earth's gravity. In the case of the gas giants, which have deep atmospheres, the tidal effects could enhance their already vigorous weather systems. Jupiter's atmosphere, for example, is characterized by strong jet streams and massive storm systems. if Jupiter were subject to strong tidal forces from Earth at close range. These weather systems might become even more energetic and complex. The interaction between the two atmospheres through gravitational and possibly magnetic forces will be a rich area for study. Magnetic fields are another important consideration. Earth has a strong magnetic field generated by the dynamo effect in its liquid outer core. This magnetic field shields the planet from the solar wind and creates the magnetosphere, a region of space around Earth dominated by Earth's magnetic field. The Moon has no global magnetic field, but some of the planets do. Mars has a weak magnetic field, only remnants of an ancient field preserved in crustal rocks. Venus has no intrinsic magnetic field. The gas giants all have strong magnetic fields, with Jupiter's being by far the most powerful. If Jupiter were at the Moon's distance, Earth would be within Jupiter's magnetosphere, the vast region of space dominated by Jupiter's magnetic field. Jupiter's magnetosphere extends millions of kilometers from the planet and is filled with intense radiation belts. Earth's own magnetic field would interact with Jupiter's, creating complex magnetic interactions and perhaps generating powerful electric currents between the two bodies. These currents could produce auroras far more intense and frequent than those currently seen on Earth, and the magnetic storms could disrupt any electronics or satellites in Earth's vicinity. The radiation from Jupiter's magnetosphere will be hazardous to life on Earth. High-energy particles trapped in Jupiter's magnetic field would bombard Earth's atmosphere, potentially damaging the ozone layer and increasing surface radiation levels. This could be another mechanism by which a nearby gas giant would render Earth uninhabitable, adding to the tidal and thermal effects already discussed. We should also think about the long-term fate of the two-body system. If Earth and a planet were in a close binary configuration, the system would lose energy over time through tidal interactions and potentially through gravitational radiation, though the latter is only significant for very massive or very close binaries. The loss of energy would cause the orbit to decay, bringing the two bodies closer together. This inward spiral would accelerate as the distance decreased because tidal forces grow stronger at smaller distances. Eventually, the two bodies would either collide and merge, or one would be torn apart by tidal forces as it crossed the Roche limit. The time scale for this process depends on the masses, the initial separation, and the internal structure of the bodies, but for scenarios we have considered, it could range from thousands to millions of years. If Earth and Mars were in such a system, they might spiral together over a few million years. As they approached each other, tidal forces would increase, volcanic and seismic activity would escalate, and the surfaces of both planets would be heavily deformed. Eventually, they might collide, creating a new, larger planet from the merged material. This planet would be molten from the energy of the collision, and would take millions of years to cool and solidify. The resulting body would have a different mass, size, and composition than either original planet, and it would have no memory of the life that once existed on Earth. If Earth and Venus were in a binary, the merger might occur on a similar timescale or faster, depending on the initial conditions. The resulting planet would be even more massive, roughly 1.8 times Earth's current mass, and would be a water-poor volcanic world, combining the worst characteristics of both planets. If Earth and a gas giant were in a binary, the timescale would depend on the gas giant's mass and the strength of the tidal forces. Earth would almost certainly be torn apart long before a collision could occur, and the debris would form a ring around the gas giant, which might eventually reaccrete into new moons or be pulled into the gas giant's atmosphere. Thinking about these end states brings us full circle to the beginning of our exploration. We began by asking what would happen if the moon were replaced by a planet, and we have journeyed through scenarios ranging from modest increases in tidal forces to complete destruction of Earth. We have explored the effects on the oceans, the crust, the mantle, the atmosphere, the magnetic field, the climate, the biosphere, and human civilization. We have considered the visual and cultural impact of seeing a planet in the sky, where the moon once hung. We have examined the orbital mechanics and long-term evolution of such systems, and we have reflected on the contingency of our existence and the delicate balance that makes Earth habitable. The answer to our question is complex and depends on which planet replaces the moon, at what distance, and under what conditions. For a planet like Mercury, the effects would be significant but perhaps not immediately catastrophic. Stronger tides, increased volcanic and seismic activity, a slowly changing length of day, and a larger, more imposing object in the sky. Life would face challenges, but the planet might remain habitable, at least for a time. For Mars, the effects would escalate. Extreme tides, intense geological activity, rapid changes in rotation, and a red giant in the sky. Earth would become increasingly inhospitable, and complex life would struggle to survive. For Venus, the effects would be catastrophic. Tides measuring hundreds of meters, continuous volcanic eruptions, rapid tidal locking, potential loss of the magnetic field and atmosphere, and a massive white disk dominating the heavens. Earth would transform into a hellish world rivaling Io. For the gas giants, especially Jupiter, Earth would be immediately or rapidly destroyed, torn apart by tidal forces, and reduced to a ring of debris orbiting the giant planet. In all cases, the presence of a planet in place of the moon would fundamentally alter Earth's physical environment and the conditions for life. The moon is not merely a passive object in the sky, but an active participant in Earth's system, and its replacement would trigger cascades of consequences that touch every aspect of our world. This thought experiment reveals the profound importance of the moon and the intricate web of interactions that connect celestial bodies. It shows us that the universe is a place of dynamic processes and delicate balances, where small changes in one component can propagate to the system with dramatic effects. As we come to the end of this exploration, we might feel a renewed appreciation for the moon that actually exists, the real moon that lights our nights, drives our tides, and stabilizes our planet. We might also feel a sense of wonder at the diversity of possibilities that exist in the universe, the countless ways that planets and moons can be arranged, and the myriad forms that planetary systems can take. Our solar system is just one example among potentially billions, each with its own unique configuration and history. Some of those systems might have binary planets, massive moons, or close-orbiting gas giants, creating conditions utterly unlike those on Earth. Each would be a laboratory of planetary physics, a unique expression of the universal laws that govern matter and energy, gravity, and motion. The question we began with was simple. What would happen if the moon were replaced by a planet? The answer, as we have discovered, is anything but simple. It is a story of forces and consequences, of stability and chaos, of destruction and transformation. It is a window into the fundamental workings of planetary systems, and a mirror reflecting back to us the specific and contingent nature of our own world. It is a reminder that the universe is both lawful and unpredictable, governed by equations we can write, but outcomes we can only sometimes foresee. And it is an invitation to keep asking questions, to keep exploring the possibilities, to keep seeking to understand the cosmos in which we find ourselves, not just as it is, but as it might be in all its infinite variety. The night sky, whether lit by the familiar face of our moon or by the imagined presence of a planet, remains a canvas for curiosity and a frontier for discovery, calling us to look upward and to wonder.